Now let us look at some other definition that is similar to what you must have seen in the continuous time case, and here things are very similar, the analogy is very close. So, we will look at even and odd parts of a sequence. X e of n equals x of n plus x of minus n by 2, and this is very similar to x c of t being x of t plus x of minus t by 2, and you can easily verify that x c of n equals x c of minus n. Any signal that satisfies this relationship, namely x of n being equal to x of minus n, it is called an even signal, and in this particular case x c of n happens to be the even part of a given signal x of n. And similarly, so this is even, x o of n is given by x of n minus x of minus n by 2, and it is easy to see that x of minus n is minus x of n, and this is the odd part of the given sequence x of n. So, any given sequence x can be decomposed into its odd and even parts, and the definition of an even signal is x of n equals x of minus n, and the definition for an odd sequence is x of minus n is minus x of n, and these are no different from their definitions from their continuous time counterparts. Just to complete this, x o of t is x of t minus x of minus t by 2. So, this we are assuming the signal to be real valued. So, this is the case for real valued signals, and there is a corresponding definition for complex valued signals. If x of n equals x star of minus n, then this is called conjugate even, and if x of n is minus x star of minus n, this is called conjugate odd. The other name that is used is conjugate symmetric, and the term that is commonly used here is conjugate anti-symmetric. Exactly the same definitions you must have seen for the continuous time case. Here if you note that if you consider e to the j omega naught n as a signal, and this is cos omega naught n plus j sin omega naught n, and it is easy to see that cos omega naught n is even and sin omega naught n is odd symmetric. So, the symmetry associated with these things, the real and imaginary parts are even and odd, very simple, which you must have seen any number of times before. On the other hand, if you consider the signal e to the j omega naught n, so this is the same as, first of all you need to replace n by minus n and then take the complex conjugate. So if you replace n by minus n, this becomes e to the minus j omega naught n, and then you need to take the complex conjugate. So this turns back into the given signal. Therefore, e to the j omega naught n is really conjugate symmetric, all right. So these are pretty simple and straightforward and follow from the definition. And let me take a simple example that is familiar to you and then point out a difference that you need to pay attention to when it comes to continuous time versus discrete time. So suppose let us consider x of n to be this signal, so this is my given x of n, and if I want to decompose this into its odd and even parts, so this is 0, 1, 2, 3. X e of n is x of n plus x of minus n by 2. What happens here is at n equal to 0, x of 0 and x of minus 0 are the same. If you add them up and then divide by 2, you will get back your sample value at 1. For the remaining 3, the even part will look like this, and this value is half. So this is the even part. And the corresponding odd part, this sample value will always be 0, and for xo of n, if you take x of n plus x of minus n by 2, right, this is the odd part. And if you add xc plus xo, you get back your original signal. There are nothing surprising here. Now let us look at this for the continuous time case. Suppose you have x of t like this, and if you try to break this up into its odd and even parts, so this is x of t plus x of minus t by 2, that is the even part. The only thing that you need to pay attention here is, before that let me assume that this is 1. And this is half. So this is the even part of the signal. And this is the odd part of the signal, so that when you add these two, you get back your original x of t. Is there any wrinkle to this? Is this fine, or should we pay attention to something? Yeah, at t equal to 0, it depends on how the signal is defined. If x of 0 is 1, then for that particular the even part is really at 0 the value will be 1, because x of 0 plus x of minus 0 by 2 will give you a value of 1. Okay. If x of 0 were 0, then the original picture stays fine. X of 0 can also be undefined, then also this picture is fine, except that at 0 the even and odd parts are not defined. Yeah, say that again. Oh, yeah, you are right. If x of 0 is 0, the even part will be 0 at t equal to 0. Yes, yeah, very good. So, the point to be noted is none of these ambiguities come about in the discrete time case, because at the origin the signal is clearly defined in the way that we expect it to be. So, there are similarities between continuous time and discrete time, but there are some points at which there will be differences, and you need to pay attention to these cases where the differences can manifest themselves.